For those of you who've been before, you've probably seen a presentation by Liam or myself about mimic design, and that's what PRFI is known for. Today I'm going to talk about something a little bit different, which is production test, and specifically high volume, cost-effective production test of mimics in the UK. Before we start, I want to acknowledge the help of my colleagues at CML Micro, whose test systems I'm going to be talking about today, and who have helped me to put this presentation together. So I'm going to start off by talking about the challenges of production testing packaged ICs, especially at RF and microwave frequencies where everything gets a little bit more tricky. How we can reduce the cost of our production testing. Some of the RF and microwave specific challenges such as test socket design and load board design. And this is where your production team talking to your design and your product team early on in the design process can really be beneficial. Then I'll talk about production test correlation, so achieving a good fit between your evaluation board performance and your production test performance. Then the test parameters that we could choose to test for our products and how we optimize that test procedure. Talk a little bit about automation, which is key to reducing cost in production test. I'll show a little video of a production test system in action as well to finish off. So firstly, why do we production test? Okay, it's to ensure that the quality of the products that we ship to the customer is guaranteed, that they are getting what they expected, there's no defects, okay, and that they can put it in their system and be confident that the product's going to work. This sounds very simple, but actually there's a complex set of considerations to take into account. Now I've shown here sort of two axes, the sort of confidence in your product on the x-axis and the sort of test speed of your production system on the y-axis. And you can go about your production test in a couple of different ways. In the bottom right-hand corner, you could choose to test everything that's on the data sheet of your product for every single IC at every single frequency. That way you can be extremely confident that every IC you ship is going to do what's intended, but this is going to be very expensive. You can imagine that all these test times are going to be very long, and that's going to add to the cost of your product. You could take another approach, which is the top left-hand corner, where you don't test at all. You just ship products straight from your assembly house to your customer. Now, this isn't going to add any additional cost to your product, but chances are there'll be a few defects. You're going to have unhappy customers. You're going to have to deal with returns. So that's probably not a great approach. The bottom left corner we can forget about, which is where you test everything, but you don't do it properly. Then you have no confidence in your product and it's high cost. So we try not to do that. But in the top right-hand corner, this is really optimally where we'd like to be. We conduct the minimum testing that is required to achieve high confidence in the product performance. And there are a few technical challenges that we need to overcome, especially at RF and microwave frequencies. So achieving correlation between the evaluation board performance and the test socket performance, and I'll go into that a little bit later on. Then achieving repeatability between our measurements. So when we get our data out of our production test system, we're going to have some part-to-part variation, but we need to be confident that that's real part-to-part variation, either due to the semiconductor process or the packaging, and it's not as a result of our measurement system. So there are several ways to overcome this. Of course, from an RF and microwave point of view, you need to calibrate your instruments. You need to have a stable ambient temperature at which you can measure at, but also these test systems are mechanical systems as well. So we have mechanical considerations as well. The ICs get pressed down into the test socket, and if that amount of pressure isn't constant, you may find that changes the electrical contact. So we have to consider that. Also, if the IC is placed slightly differently into the test socket each time, that's going to cause a small amount of variation as well. And that might be the difference between a pass and a fail for your IC. And then because we've got moving parts, we may have bits of debris that come from the package, for example, or the test pins wearing out. This could potentially short out a pin and give you an anomalous result, or there could be just dust, and that again changes the contact between your test pin and your IC. So there are lots of things to consider here. And then another technical challenge is reducing the impact of the test socket and the PCB on the performance of the IC. This test socket is an extra layer effectively in between your IC and the board, and so trying to minimize the impact of that becomes an increasing challenge at RF and microwave frequencies. So at this point, some of you will be thinking, well, this sounds a bit tricky. Why don't I just get somebody else to deal with this problem? And that is a perfectly valid question. There are a few things to consider. So the obvious one is labour costs. So if you're testing in the UK or Europe, your labour costs for your production test operators is going to be higher than, for example, in Asia, where a lot of production test carries out. And if you're testing a single product and you're expecting to be shipping tens of millions or hundreds of millions, and you want the lowest cost possible, this is probably the right way to go. But it's not necessarily the right case for all scenarios. We also have to consider supply chain resilience. And in the past few years, this has become much more of a hot topic and will probably continue to be for many years to come. So if you're taking control of the end part of your supply chain before you just ship to your customers, you can potentially smooth out any bumps in your supply chain. You can combine this with your inventory management, and hopefully that means you can get a steady flow of products going to your customer. There's flexibility as well. Now, when you test and you outsource it, you'll probably have a contract in place to test particular parameters, particular products, and then the test house really just wants to be doing the same thing over and over again. But if you have a special order from a customer, for example, who wants more extensive testing than what you normally offer, it may take time to agree that with an outsourced test house. You have to speak to their commercial department, speak to their technical team. If you do it in-house, you can be a lot more flexible. And kind of tied to that as well, the speed at which any issues can be resolved. Now, you're always going to have some issues in production test, especially when you're bringing a new product to market. But if you can just walk down the corridor and speak to your production test team, and they can come and speak to you, and you can resolve issues quicker than, for example, having to deal with an 8-hour time difference with Asia. And you might find that then, it takes a while to even schedule a call when everybody's available. If you're in-house, you can respond a lot more quickly and solve your issues, any issues that do arise. And then finally, reputation as well. So it's sending a message to your customers saying that you care so much about the quality of your products and guaranteeing that they're going to be shipped properly, that you're actually managing it yourself. And that can be a big selling point to customers as well. So in summary, in-house testing is really suited to a broad product mix where you need the flexibility to switch between different test setups quickly, different products. You still want to do this in high volume, but it's well suited when you have multiple products, and for example, CML probably 100, 200 products, and you want to be able to switch quickly between those. So doing it in-house is a lot more flexible than outsourcing it. Having said that, we still want to do this at a competitive cost. Okay, customers aren't going to want to pay a huge premium for you doing the testing in-house when it could be much, much cheaper to outsource it. So we need to think about how we can reduce the cost of our production test. And there are a few key things that we consider. So reducing test time per IC, that's obvious that if you can reduce the test time per IC, you can test more ICs, and so the cost per unit comes down. Key ways to do this are using auto handlers to handle the packages, place them into the socket, and then pick them up when they're being tested. And I'll show a video of that later on. And the system actually that the videos are shown on is shown on the right here, where you've got the auto handlers on the left and the tray handlers on the right. Reducing the number of parameters to test can also be a way to reduce the time and therefore reduce the cost. And I'll talk about how we select that later. And then the measurement test equipment settings themselves. Does the bandwidth that you set your measurement instrument to, does it need to be that particular bandwidth? Could you ease it a little bit and therefore speed up your test time? And shaving, even half a second off a measurement, you can see how when you're testing potentially thousands or millions of devices, that's going to stack up pretty quickly. Another way to reduce the cost is to increase the automation, and I'll talk about that later. And really the key there is your production test operator can then run multiple test setups in parallel, simultaneously, and just be keeping an eye on them, but they're pretty much running themselves. And then maximizing uptime of the systems themselves. Okay, so if the system is down, it's not testing anything, that's limiting how many ICs you can be testing per week or per month, and then that directly translates to the cost of that per IC. So what can we do? We can do preventative maintenance. So things in your production test system will wear out, like your test sockets. Do you know what the lifetime of those test sockets are? And are you replacing them just before you need to, rather than waiting for them to fail, finding there's a problem and having to diagnose that problem. You could also try to reduce the changeover time between products. And if you have a broad product mix, maybe you test a batch of one product, then you need to quickly switch with the same test system to a batch of another product. Okay, you don't want to be hauling lots of measurement equipment around to be able to do that. You don't want to have your test system down for a day whilst you're switching over. You want it to be much quicker than that. And what I've shown at the bottom here, this is an entire RF microwave instrument test system built into a single chassis. And this is on wheels, so you can move it between handlers very quickly. It's all self-contained, so you can plug it in and get going much quicker than carting lots of equipment around. And then this also uses a common hardware platform with commercially available measurement cards. And that maximizes your uptime, because if you do have a problem, you can wheel this system away, you can wheel another one in and get going with your production testing again, then go off and diagnose your problem with your test system. And if it's a particular one card that's gone wrong and it's commercially available, maybe you already have a spare one in stock, or maybe you can order it on a couple of days turnaround and you can get up and running a lot quicker. So having a common hardware platform as well maximizes the uptime of your system. So from a technical point of view, we need to be thinking about normal sort of RF and microwave challenges and how that translates to our test socket design. So the test socket I'll show you later. It sits on a production test PCB, and it's what the IC interfaces with in order to be tested. Now, you're never going to get the same performance with a test socket compared to soldered to an evaluation board. But if you design it right, you can minimize the impact. And this particular design is based on pogo pins, and that's what's shown on the left. This is effectively a spring-loaded pin that when the IC is pushed onto the test socket, it compresses and you get a good electrical contact. And the test socket that I'm showing here, this is for a 3x3 QFN package with 16 leads. It's got 16 pins around the outside, and then it's got 4 pins that interface with the exposed paddle. And there's a solid copper block in the middle as well. And this works pretty well up to about a gigahertz or so. You can see how the pins of the IC then map to the pins of the test socket. But there are a few things that are limiting the frequency performance of this socket. So for a start, you've got 4 pogo pins which interface with the exposed paddle. That'll give a relatively high source inductance. What that means is you can have feedback between your output and the input if you're testing an amplifier, and that can have a negative impact on your stability. It'll also degrade your input and output return losses. The actual copper itself is relatively limited compared to the side of the exposed paddle. Now, for a low power device, that probably doesn't matter, but if you're testing a high power mmWave IC, especially if the efficiency isn't that good, you would ideally like to have more copper in there to help you conduct the heat away. You've also got the RF pins, which here look like a little bit of series inductance, and that's going to degrade your return losses as well. So this was the initial design that was used up to 1 gigahertz. But for the same package, there was a revised design that was done that works well up to 30 gigahertz. And there are a few key changes here. So firstly, you'll notice that there are 16 pogo pins used for the exposed panel compared to 4. That's reducing your source inductance. The RF pins now, rather than just looking like a series inductance, actually have got a bit of coax, or they look like a bit of coax because they've got a bit of dielectric around them. So that's designed to be as close to 50 ohms as possible. So your transition between your PCB and your IC is a 50 ohm environment. So that's very beneficial as well. And then you'll see that it's mostly a fixture that's made out of copper with a bit of dielectric in there for insulating the pins from one another. But there's a lot more copper there. That's going to be much better for getting your heat away. And again, that maps onto this IC pretty well. It's exactly the same package, but it works better up to 30 gigahertz. And this is really where your design team talking to your production test team early on can really smooth the flow from going from your initial evaluation through to qualification and then through to the product actually being fully in production. Your design team will be able to advise on the effects of, let's say, the source inductance or a bit of series inductance in there, advise on whether existing test sockets might be suitable or whether a new one needs to be redesigned. If it needs to be designed, that can be happening in parallel with the IC rather than having your IC ready to go and then thinking about your production test socket. Okay. And of course, if you can use existing test sockets and they work up to the frequency you need to, maybe that influences the design or the decision on which package to use really on in your design phase and can lower the cost of the product as well. So another area where your design team talking to your production team and your product team can really help is in the load board design. So if we just point out some of the pictures here, then the IC under test is here in the middle, sitting in the test socket. The test socket itself is marked by the yellow area, and you can see that that's actually restricting where we can put components. I'll talk about that in a second. And then you've got the load board itself. So in the load board design, there are a few factors to consider. So the test socket footprint versus where you want to place your SMT components. If you design an evaluation board, you can put your SMT components wherever you like. If you've got off-chip matching, you generally want to put that pretty close to the device. You might not be able to do that with your load board design. So simulating the effect of that early on is very advantageous. Even if you've got a 50 ohm in and out device and you don't need any off-chip matching, you're probably going to need some sort of decoupling component, especially if it's an amplifier, to keep it stable at low frequencies. If those low frequency decoupling capacitors are moved further away from the IC compared to your original design, is that going to cause you any stability issues? Okay? Again, that's worth knowing about so that you can perhaps modify your load board design before that becomes an issue. Then the PCB stack up for a production test environment. You want something that's pretty robust. It's being moved around. It's being plugged into different systems. Maybe you want a thicker PCB for your mechanical stability. However, perhaps that's not the best for RF performance, and perhaps it's not best thermally. And again, having these conversations early is very beneficial. Then do you need to be using the most expensive connectors that need to be torqued up to a specific level, or can you get away with using push-on connectors, for example, that's going to be much easier to set up, going to be much cheaper, depending on what frequency you're working at. The general ease of use of the board as well. How easy is it for a production test operator to put it into the system? With the DC connectors, can they be connected only one way, or could you potentially get it the wrong way around? Then you'll be wasting time diagnosing problems that aren't really problems with the test setup at all. And also trying to ensure commonality with other production test boards that you've done. If you've got a broad range of products that you're testing, your production test operators aren't going to want to have to memorize the details of every single production test board. If you can keep it as common as possible between the boards, they can just get on and test it. And again, the setup time and the changeover between testing different products can be greatly accelerated. So one of the other challenges is production test correlation. And here I'm showing some real test data from the systems that CML use. And what we're showing here is the performance of a device under test when it's been put into a production test board, like the one I showed earlier, and that's in blue. And then the performance when it's actually soldered onto an evaluation board, shown in orange. Now, it's important to note that on the x-axis here, these are specific device under tests, okay? And these are laser marked, so you're taking the exact same IC, testing it in your test socket, then picking it up, soldering it down to your board, and checking how it works, okay? And so ideally these lines would sit on top of each other, but as we've discussed, the test socket has some negative effects on the performance. But what you're really looking for is a constant offset against each device so that you can say, well, if I'm measuring, let's say, 31.5 dBm in production test, I know that that correlates to about 32.5 dBm in real life performance when you solder that down to a board. And the same ICs have been measured across 3 frequencies, so low band, mid band, and high band. This is the output power at P1 dB compression. You can see the difference between the evaluation board and the production test board increases slightly with frequency because all of the effects that we talked about just get worse as you go up in frequency. But across 10 devices that have been tested, there's pretty good correlation between what you're seeing on your production test board and your evaluation board. And of course, to get more confidence in this, you can do this across even more devices, so it's more statistically significant. Then when we're starting to think about setting up our production test system, we've got a number of different parameters that we can test. Okay, you probably want to be testing your DC parameters to check your IC biases up properly. Maybe you want to test it in some kind of standby mode as well. But that's not going to tell you anything about the RF performance. So you probably want to be measuring the S parameters as well. Now, if you're just looking at a low power component, maybe that's all you need to test. A lot of the time we'll be testing things like amplifiers. You want to know what the large signal performance is like. Okay, so that increases the complexity of your test setup already. But then, do you want to test this CW, which is thermally quite challenging, or do you want to test it pulsed? Pulsed is even more complicated, so that's adding to your cost, adding to your setup. Then you will probably, for a comms application, be trying to put some sort of modulated signal through it. Do you want to measure it two-tone performance, just simply measure the IP3, or measure the modulated signal performance as well? Again, this is increasing the complexity of our test setups, increasing our test time, and we need to think about the time taken to conduct each measurement, the test equipment that is required. We're going to have to go out and spend lots of money for our test equipment. Do we have automated software that can measure this, or do we need somebody to develop and test and debug this? And then are we going to test in each mode or configuration of the IC? So it might have a high gain mode and a low gain mode, for example. Do we need to test in both? If we're testing everything in both, we've automatically doubled the number of parameters that we're testing, and we've doubled our test time. So how do we go about optimizing this test procedure and selecting what we want? So obviously the key question with all of this is what's important to our customers, and some customers may have more stringent requirements than others. This is where the flexibility of having an in-house test team can really help, because it allows you to change the test routine for different customers. So some may have more stringent requirements than the others. If we're looking at how we get to this top right-hand corner where we do minimum testing to achieve the high product confidence, well, we would start by testing everything and really having confidence in the product, making sure that what we're shipping to customers is all working properly, even if it's costing slightly more per IC than we would ideally like. That's still going to be better than shipping defective products and having to deal with unhappy customers. So we'd start off with testing more parameters, make sure that the IC is working properly, and then really gathering data from our production test system on how these products are performing. Once you've gathered sufficient data, you can start looking for patterns in this test data. So, for example, if you're seeing fails in your ICs, is it just slightly failing, or is it just not working at all? Okay, if these devices aren't biasing up at all, maybe we can skip the rest of the tests after DC and just put that IC in the rejected pile straight away. We don't need to bother measuring it S parameters because they're not going to pass that either. So we can look at that as well. Do we find correlation between different test parameters? So, for example, we might be measuring IP3 and we might be measuring output power. Well, you may find that every time output power passes, IP3 also passes. And conversely, every time output power fails, IP3 also fails. So do we really need to be testing both if they're telling us the same thing? And the more devices you test, the better the correlation and the better confidence you can have in this. Okay. And then really trying to move up to this minimal testing, trying to reduce the test time to speed up the throughput. So we can find out which parameters take the longest to test. Are these parameters that we actually need to be testing? Can we change the settings to reduce the test for these parameters that are taking up most of your test time? Could we reduce the number of frequencies that are tested? Maybe we start off testing at 5 frequencies. Can we get away with testing 3? Or do we find that, for example, at the higher frequency, that's where all the fails happen? Maybe we can get away with only testing at 1 frequency, and if it passes for that top frequency, perhaps it passes for all others. But you need to be collecting the test data and analyzing it really to optimize that. And can we eliminate a test parameter entirely? Like I say, maybe if we can get rid of IP3 and we can just test everything single tone, that's great. That simplifies our setup. It reduces the cost, reduces the time to test as well. Okay. Then production test automation. So the aim of this is really to increase the number of test systems that each operator is running simultaneously. And the biggest advantage of this is to use a package part handler, which is picking up the devices and putting them down by itself. The test operator can then just leave it to get on with itself, and you put a tray of parts in, it tests them, and then at the end you take the tray out. Okay, but if you could automate the tray handling as well, so you could stack several trays, and it can then handle when it's tested that, moving it down, putting in another tray. CML have systems that can test up to 30 trays. So that's automatically going to reduce the amount of times that your operator needs to go back and change the tray. The system can just be running and doing your production test nice and efficiently. You can also automate the data storage and the analysis and the reporting. So like I was saying, we want to be collecting data on each of these ICs, look at what our pass and fail rate is like, storing all the measurements, and of course we can do that automatically. But we also want to analyze and report it in real time. And really what we want to do is distill all of the measurements down into a single number, which is just a yield rate expressed as a percentage. Then we want it so that your production test operator can just walk past the system, they can look at what the yield rate is, they can think, is that what I expected it to be? Has it gone up? Has it gone down? And then they can intervene if necessary, but if not, they can just carry on by. And then also automating the measurement system reliability and error reporting. So if there is a software or hardware problem, is the data stored automatically and is the progress saved? If you've done 29 trays out of 30 and then there's a problem with the system, do we have to go back and retest all of those, or have we automatically saved the data? Are the error messages easy to understand and fixed by the operator, or do they have to call up the person who originally set up the production test system? And then does the system automatically advise on when maintenance is required? So it's telling you you're getting close to needing to replace a part or to do some maintenance, rather than waiting for it to fail, and then possibly your automation, your maintenance is going to be more extensive. So bringing this all together, I'm going to try and show a video of a production test system in action. Before it plays, I'm just going to point out some of the features. So we've got two package part handlers here, imaginatively labeled 1 and 2. Part 2 is waiting for the device under test to finish testing, and the handler 1 has got a part ready to test and ready to go. So I'm going to play it. This is actually testing a mixed signal part rather than a pure RF part, so the test time is quite a bit longer. It's about 20 seconds or so. You can see what it's done there is it's picked up the old part, immediately put in a new part, so that there's no time wasted and the system is always measuring. It's then come back, picked up another part, it's put it into these what are called preciser plates, which make sure that the IC is put in the test socket the same every single time. And it's now testing, it's waiting for the next part to be tested, and it puts it in straight away. Okay, then it goes off and gets another part. Okay, you can see really you're trying to use the system as much as possible. You're trying to minimize the amount of time that the system's sitting there doing nothing. And then the other end of this production test system, this is a much shorter video. This is just the heads putting down a device that it's tested and picking up the next one. And you can see again, you've got on one side, you've got all of the tested parts, and on the other side, you've got all of the untested parts. And of course, it's really important to make sure you know which is which when you're loading and unloading your trays. Otherwise, you might be wasting quite a lot of time. So just to sum up, the test sockets and production test boards have a greater impact on production test performance at RF and microwave frequencies, and that requires careful consideration. Automation is key to keeping your production test costs nice and low. Often when you're starting out, the production test is a compromise between confidence in your product and the time and the cost that it takes to test. However, if you carefully consider which parameters you need to test and you collect data on this, you can achieve low test costs and high product confidence. And then close collaboration between the design team and the production test team can highlight any potential issues earlier and help you get into production much earlier. So if you want more information about PRFI's design services, you can go to our website, prfi.com. For all of the systems I've shown today have come from CML Micro, and to find out more about their products, which are all tested in their facility down in Essex, you can go to their website, which is cmlmicro.com. And thanks very much for your attention.
Thank you very much, Rob. That was really interesting.
Good.
I'm sure there are a few questions.
Yeah, I mean, You you're talking about how to save money with testing, but as kind of glaringly obvious is possibly that you didn't mention parallelism at all, parallel testing, in order to save cost.
Yeah, I mean that is another way to reduce your cost for sure.
Okay.
Sure.
But we got any kind of comments on what the trade-offs are or this?
Yeah, so I mean, if you're talking about testing multiple ICs in parallel, I mean there are multiple test setups running, in parallel with these. So I've just shown one here. You can, with some of the systems, you can be putting handlers into multiple sockets, things like that. It's really a trade-off between the initial cost and then the test time. But that really depends on your volume. If you're going to really high volumes, then definitely doing it in parallel is the right way to do it. Sure.
In that, with confidence of your tests, the test time optimization, have you used any AI and deep learning to determine which tests you don't need to do because they don't find any failures?
Not as far as I know.
Also, kind of conspicuous by its absence is wafer test. When you consider wafer testing your product, opposed to just package testing, because package testing obviously comes with its own risks of overhead costs of packaging, which don't end up getting due.
Yeah, no, that's a great question. So you can do that. So CML, for example, wouldn't do the RF and wafer testing themselves, but of course you can get your foundry to do that. That really depends on a few things. Well, what's your yield? Maybe you want to do the RF and wafer test to begin with, find out what your yield is at the wafer level, and then see what your yield is at the package level. Okay, and if those are comparable, maybe you can just do RF and wafer testing, or maybe you can just do packaging. But to increase confidence, you could do both to begin with. Also depends on your packaging costs as well. If your packaging costs are high, and then you're paying a lot for that package, not them finding the chip itself was defective, that's a waste of money. If your packaging costs are low, maybe you say, well, it's only a few cents to package it. I don't care if I waste it. But yeah, it's definitely a trade-off. It depends on volume. It depends on test costs from the foundry and your production test costs as well. But yeah, definitely a consideration.
Okay.
Yeah, I think the big thing is obviously calibration. Is there a way where that you would decide how often to calibrate? Because obviously calibration can take quite a lot of time. So, but you also want to minimize that. And how do you handle that?
Well, you can look at the data that you're getting from your test system, right? So you might find that there's a gradual drift in the average performance that you're getting from your ICs. And if you know that you've got tested enough samples and you've got a good idea and it's drifting, maybe that's a sign that it's a measurement thing. Maybe you just schedule it every, how often, and you find that if that's sufficient and you're not seeing any problems, you try calibrating a bit less often, see if you've got any problems. And trying to reduce it. So, and probably talking to the test equipment manufacturers as well helps. Again, if you're keeping like a stable temperature environment, that kind of helps as well. Your instruments will stay in cal for a reasonable amount of time. And if you're not moving them as well, not moving the cables, it stays valid for longer, your calibration.
Okay, just one more. Johnny.
So just to reinforce that question, so typically before trying and weekly testing, you'll have test golden devices. And you might need a golden performance. So if that starts to drift, then it's time to recalibrate.
Yep.
Typically, it'd be around 3.
Yep. Yeah. No, thanks, Jerry. No, that works as well, definitely.